morning. Hope you all can hear me okay. So I'm Pat Warner from Lotus F1 Team, Brett Lyons from Boeing. We spent a number of years collaborating on a number of projects throughout our companies, but the additive manufacturing one has been the one that's really taken hold and has kept us going since we started in 2004. So our two companies aligned pretty well. A lot of people don't quite understand the synergy. But when we started looking at everything, we really lined up well in our technologies, our manufacturing methods, and our requirements from parts. So this presentation will go through that. We'll start off, I think, next with a little video that basically shows the background of what we've done and what we've achieved, and then hopefully we'll expand upon that.
This is the fastest vehicle development environment known to man, and that's really valuable for Boeing. And it might not be obvious because one company's building a car, we're building aircraft and satellites, but we have some really good overlap. Boeing and Lotus F1 Team have been working together in additive manufacturing since 2005. Additive manufacturing is building parts directly from 3D data. 3D printers, as they're commonly known, so there's no tooling involved. Additive manufacturing starts from the bottom up and grows the parts layer by layer by layer by layer by very selectively applying energy to the material. So this is an airfoil detail on the Lotus F1 car. The challenge there then is how do you get reinforcement to go in all different directions? We figured out a way to take recycled carbon fiber from Boeing production and then integrate that into the material such that when we spread the material into the machine, we have fibers going in all different directions. We found that we could make a better part like this by using additive manufacturing. And we know that the mechanical performance is uniform in all different directions and locations on the build. On a F1 car, they put all these aerodynamic details in the car to generate a lot of downforce to keep the car on the track through some really tight cornering maneuvers. And on our aircraft, we're using aerodynamic elements to generate lift. But it's a big difference when you're going around track at 200 and some miles an hour, getting bounced at 5Gs side to side for 2-3 hours on end. That's 5 times the force of gravity worth of acceleration that is applied to the driver and every single component on the car just by going around the track. I mean, that kind of testing would cost us just a tremendous amount of money to simulate, and these guys do it every week. Every year, Lotus F1 Team produces a new car, and they work at just an amazing pace to react to the demands that they have in racing. And we get the chance to actually test these things out a lot faster than we would normally at home because Lotus F1 Team's product development cycle is so fast. As engineers, I think 30% of your job is to worry. And then the balance of that, hopefully, is curiosity. And one of the things that both Boeing and Lotus F1 Team get to do is we really get to challenge physics. We really get to push against nature, to go faster, go cleaner, on all sorts of different fronts. When you look at that car and you know it's been influenced even just a little bit by some of the work that you put in, it's tremendously satisfying.
Okay, so stepping back a little bit, we got together in 2004. Took a little while to figure out what we were going to do, what we were trying to achieve, which of our technologies aligned, which ones didn't, what targets we were going to go after. Additive manufacturing came out really high on that list. The parts on the left are Boeing, the parts on the right are Lotus, and they were very similar. That obviously helped us in setting the set targets and what we wanted to achieve and where we wanted to end up, which was troublesome. So we looked at our systems that we had in sight. Fortunately, Boeing had the same systems, so that lined up pretty well. So we started aligning all our testing methods, building parts basically so we could move them from site to site and build the same part at any place on anyone's machine. That presented rather a challenge. Most of these machines are kind of unique, even though they come off a production line. No two seem to be the same. So we spent some time figuring out what we needed to change, how we needed to send parameters to different sites, so the part we built in one machine would have come out the same as the part we built on another machine. That was quite critical for these guys more than us, because they outsource quite a lot, whereas we tend to keep ours in-house and do everything on site. But being aligned with them taught us a lot along the way of how to improve what we were doing, how to get the best part out every time, not just one or two good bits and one or two not so good bits. We started looking at the maximum performance we could get out of each material we had. And we came on quite a long way in the first year of our collaboration, in that the parts we were making had much better material properties than those generated off the standard data sheets supplied by the material manufacturers. We spent a lot of time looking at our laser parameters, our scan strategies, and how we could make every part perform to the maximum level, which is quite important for us and more so for them. We don't like it when parts fall off the car, but it's not quite so critical as it is for these guys. We soon realized that material systems would limit what we could do. Don't get me wrong, there's some very good materials on the market. They have their place and we use them all. But if we wanted to go a bit higher, a bit further, use things with a bit more load, a bit more structural, we needed to change the materials we had, or at least modify them in a format that suited us. So we set about what we could do to improve things, what our targets would be. Higher temperature materials were an obvious gain for us. The average temperature under the engine cover of a Formula One car is about 135 C. You start moving closer to brakes or exhaust and it gets a lot hotter. So we were pretty on the limit of what we could do already. We had to be very, very careful of where we placed rapid manufactured parts on a car. And so we started looking at higher temperature systems. At this point, none of those existed. So we took an existing machine and basically pulled it to pieces. The architecture of the machine that we bought was suitable to go higher temperature, but all of the systems within it weren't capable of it. So we replaced all the heater systems, replaced any items that were thermally vulnerable, replaced the laser, we replaced the scanning system, the computers, and found that we could build parts significantly, or we could use materials significantly hotter temperatures than were currently usable. That did present some challenges along the way. All the issues you have with laser sintering of thermal bleed and temperature loss during the build were massively extended due to the higher temperatures we were running. So we had to start looking at specific heater systems with zoned heating. So the heater you can see on the slides there is controllable. Every element, you can set the temperature, the amount of power coming out of that. So you can balance the whole bed and get a nice thermal distribution, which is quite critical to laser sintering. So now we had a functioning machine. Where do we go from there? So we chose some key materials that we thought would be usable to us. We had our successes and we had our failures. We had a lot of failures. We started off thinking that polyamide would be the way to go, because we all know how to process polyamides in an SLS machine. Turned out not to be the case, and the polyamide systems we were choosing didn't come out as well as we'd hoped. Our engineers all like PEEK. It performs massively well, doesn't really sinter particularly well. So again, we went down that route, we fell over. So we had to start moving along. I won't go through the whole list because it's quite extensive. We ended up with PAKs, PEKs, a number of different materials that would operate in the temperature regions we were looking in the machine, but would also operate on our vehicles at the kind of temperatures issues we had to deal with. So we've been putting parts on race cars since 2003. We had to limit those due to the materials we had. Very low risk areas, low load areas. parts that if they fell off weren't too detrimental to us. And we had our hiccups along the way for sure. We learnt a lot. We basically started targeting electronic systems, small cooling ducts, things that were on the inside of the car and could be well supported without being critical if we had a failure. We've moved on a long way since then. So the slides you see at the bottom, the photos you see at the bottom, are all current SLS parts on cars. We use them in our braking system, which gets very, very hot, particularly when the car's static on the grid. It's all heat soaked then. The temperature's moving around through the parts. We were getting a lot of creep and movement. We've eradicated a lot of that. Aerodynamic components on the front wing, aerodynamic components on the engine intakes, lots of cooling ducts and electrical boxes around the engine itself, which we couldn't previously do. So the advances we've made have been pretty good for us. There's still a long way to go, we believe, and that's basically what we've been targeting along the way. And it doesn't always work out for us, but every failure is a lesson learned, and we move on from that, find out where the failure was, in a similar way to these guys do reconstructions of crashed aircraft, which they hopefully don't get very often. We analyze every part, bring it back to the factory, figure out what we did wrong, how we can correct it, and move on from there. Over to you, sir.
Thanks, Pat. So when Pat talks about analyzing mechanical properties, understanding the performance of said materials for their use on aircraft, it's hard to overstate how much work goes into that at Boeing and all major aircraft manufacturers that have to certify parts. But really, the working in aerospace has provided a great opportunity to really apply a high amount of rigor to a material system and processing system, additive manufacturing, that hasn't really received it in its, at least in its first 2 decades. So at Boeing, we do full design allowables, full mechanical testing. That's as required per the FAA. FAR 25613, for example, tells us we have to understand the performance of a material in any given time throughout its lifespan, including all defects of manufacturing, et cetera, et cetera. So it's very important to us to understand how those materials work, and it's also then from an economic perspective important to think about additive manufacturing and how we can really leverage its advantages. In particular, when we thought about going to higher strength materials with reinforcement, we realized that our economic model for using additive manufacturing, and by that I mean the flexibility that allows us to do a very small quantity of parts, spare parts, whatnot, emergent needs, to satisfy emergent needs, doesn't allow us to go in at every little detail part and do a ton of engineering. We can't say, okay, well I know the modulus is 3.2 GPA in X and 1 in Z, and I have to orient the part such and such. There's just no engineering budget to support that. So for additive to work in aerospace, you really, really want an isotropic model. That holds true for, I should say, the technologies that are available now. There's stuff in the future where the part value is higher to the point where you could actually consider it, but for the foreseeable future, really, you want an isotropic material. It's critical. It allows the supply chain to nest those parts as economics dictate. So then you get your part fastest and you get it for the most reasonable cost. We are very cost sensitive in aerospace, believe it or not. Each 777 we make has about 3 million parts, right? I mean, it's just a huge amount of work. We fly, we build a few thousand, several thousand additive parts per year at our supply chain and get them delivered on that. So that's still small peanuts, but every little part is watched within Boeing. So we really have to understand what those properties are, understand how that affects the economics of the whole process. So as I mentioned, we get a lot of parts in that are produced to specification for both Boeing commercial aircraft and the defense side. And the reason why we use it, hopefully in this audience, is obvious, so I'm not going to belabor it. But needless to say, when it was about 2001 or so, when I went into my first manager's office and asked for money for a 3D printing machine, I had to go through this in pretty exhausting detail. So looking back, it's nice to be in an environment like this and see how the technology's grown. A few details on the economics of it. When you think about one little simple part for an aircraft, be it a diffuser like that or whatnot, that's tens of thousands of dollars of tooling that goes into it. Months and months of flow time, logistics, et cetera. That's one of 3 million parts, right? So you start multiplying that and you can see what effect additive can have and why we've been investing in it for so long. And then when you think about any change that you'd have to that part, obviously that starts that whole cycle again. So again, multiply everything I say by 3 million, and then hopefully it's clear why we work in this area. So as I mentioned, and is publicly disclosed, Boeing's been flying flight hardware for aircraft since 2002, both on the military and commercial side. So you see there's some public references there that you can see. We have specifications, we have allowables, we have supply chain, we have people pushing on cost reduction already. That kind of gives you an idea of where the maturity level is in the industry. We had quite limited materials, as Pat mentioned. So we began working in, I think it was 2006 when we started the high-temp work. Yeah, started building our own machine because no one could do it, and if F1 and Aerospace can't do it, then who can? When we started looking at higher performance options, obviously the natural place to look with polymers is in reinforcements, right? You only get so much out of neat resins. And we started to look at what options were out there. There were some dry blended materials at the time, but as you see from the SEM image on the top, a dry blended material induces two kind of significant problems. One is anisotropy. So you've got all your fibers going over like a big comb over in the machine, giving you properties that are really good in one direction and horrible in the others. That works well if you're making like a UAV spar or something like that, right? There's a few parts where you want that kind of thing. That's really preferential. But again, for our model of building parts where we want to have as much freeform capability and supply chain logistics as possible, that doesn't work. Like we can't rosette for an interior lining part that we're going to make 12 of like we would a wing skin composite. You can't put that much GD&T and inspection requirement on a systems part as you would a big composite part. So the dry blend materials really weren't an option for us, either the spherical reinforcements or the fibrous reinforcements. The other problem is if you've ever worked with raw milled carbon fiber, raise your hand. I mean, it's just horrible stuff to deal with. It is a legitimate health and safety issue, but also that's a very conductive, very fine material. So if you start peppering that around your machines and you want them to run every day, you've got a kind of fundamental problem there. So we thought long and hard and tried some different solutions to reinforcement. What we ended up with was an encapsulated material. So this is what we've been working with in a few polymer matrices, but basically the gist of the method is that we take the fiber, we mix it with the polymer in such a way that each little particle that we have in the machine actually has fibers embedded in it. So imagine you're the mean kid on the block and you make a snowball with sticks in it and you throw that at your friend. That's basically that's the material model. The reason why we do that is that when you roll the material out, then you get basically with a generally spherical particle, you get a generally isotropic orientation of your fibers, and your modulus and mechanical properties are commensurately isotropic. There's still a little bit of knockdown in Z because you have still a stair stepping and layering in a powder-based process. So you get about a 10-15% knockdown that way, but that's close enough. And particularly in modulus, when you talk about from a design engineer's perspective, you basically have your stress strain curve, and if your moduluses overlap, right, you have a little bit of truncation on your strength, but that's a designable isotropy. So here you can see just some images of some of the materials we've made. Again, we've got a few different matrix materials. We work with Advanced Laser Materials. They're here, and Rick Booth's one of our co-authors. Here we've spent years and years and years going through different formulations, peaking and tweaking. We've got two formulas come out. One's a polyaryl and one's a polyamide. So we've had extensive use of both of them. Pat's used the nylon more so, and we've used the PEC more so, but we've got it on our plate to be able to put on the car and the jet, respectively. And here you can see a few examples of both. You can see it processing. The micro CT images down on the bottom are kind of unique. Those are actually, it's a computed microtomography of like a, I think that ends up being like a 100 micron square or something like that, that shows actual individual filaments. So that you can see the random orientation of those filaments, that little bird's nest of the thing. That's basically what the reinforcement looks like throughout the part. You can see it in cross-sectional micrograph above. That doesn't really kind of tell the picture. We started working with the tomography because it gave us a lot more information. You obviously notice it's a fully dense part. That's the thing about laser sintering. It's why when you're really getting your serious applications with additive, it's still powder bed thermoplastics for polymer side. There are a lot of new neat technologies out there that are growing though, so that's great to see. How do we end up? So Boeing policy doesn't allow me to put material properties in presentations, so what we can do is just generally normalize the things. But this is basically kind of gives you an idea of what we've achieved with the material approach that we have, with the polyaral and the nylon, respectively, with their trade names from ALM. So if you normalize to a nylon 11, like nylon 12 standard, they're very similar properties. In ultimate strengths, again, with such a fine milled fiber, you don't get a ton of strength increase on the matrix. The matrix is a little bit stronger with the polyarals, for example. But as you can see with the nylon 11 there, you're getting about a 20% increase in strength. Not much in strength. Where you start gaining things is in more subtle ways. So there's your Z modulus, obviously, that's, again, right about the same for the nylons there. But the Z modulus in tension is really the kind of limiting sizing factor normally. So those are the points where you have to really look. So you're getting about 3x increase in modulus in the polyaral with a TG, which is almost 3 times higher, right? So now you start thinking about the application space that opens up, where you've got 3 times higher modulus and 3 times greater approximate temperature capability. That gives you quite a bit more room to move. And then with a nylon, you're basically functionally doubling your modulus, and you get a lot more temperature capability if you look at heat deflection data, which isn't here. The other aspect that we have in the commercial aircraft side is flammability. So with the polyarals, they meet and surpass all the flammability requirements we have inside the cabin. I think most people would be, hopefully you'll never have to see this, but you'd be surprised how hard it is to induce negative responses from a flammability perspective with the polyarals. It's really hard to burn these things. They're really, really stable materials. So literally you can start putting torches on these things that started out as gasoline basically at some point in their past, and they're so chemically stable that they do well. So that opens up between the modulus and the flammability and the temperature capability, gives a lot more room to move and a lot more places to apply your additive parts. So one of the things we do with our technology readiness level development is we do producibility demonstrations at Boeing. So we've used Boeing's eco-demonstrator program. So this is basically a multi-aircraft program that exists within Boeing Commercial Aircraft Product Development that gives engineers and program managers an aircraft to work with every few years to put new technologies on. It's really great, especially in a big giant company like Boeing, to have this kind of flexible program. These aircraft are flown on experimental tickets. We do put the same amount of rigor we put on our commercial aircraft, given the scope of the flight test programs that exist. So these aircraft will fly for a year and a half or something like that. But we go through full safe to fly reviews. We have FAA oversight and whatnot. And we do a lot of neat technologies with them. The 737 aircraft you see there had some winglet work on it, had some fuel cells, for example, a bunch of flight deck instrumentation changes and whatnot. The 757 had a large number of aerodynamic changes, pretty significant ones. We had some laminar flow rate related technologies on that airplane, which required quite a bit of rebuild. Some interior tests. We have new sidewall panels, for example, et cetera, et cetera. I could go on. The 787 program had some really neat things from a manufacturing side and control side. But what I want to focus on, we've had additive parts on all of those, because again, within Boeing, additive manufacturing for prototype and even for production is fairly ubiquitous now, given the application scope that it has. For the 57, what we did is we took our new polyaral carbon fiber reinforced material, and then built what you see there is what we call the aft aisle stand. So this is basically the whole tub that holds all your instrumentations and flight controls aft the throttle quadrant. So it's a pretty big part. It's yay big or so. And we made it in, again, it's a polyaral carbon fiber material. We used the big high-temp machines from EOS to build it, assembled it, finished it. We went through a 13-point safe to fly review for that part. So we did full FEA, impact, abuse, loads, egress analysis, et cetera, integration with all the systems that were there that requires EME. You have to go through appearance requirements. We're not going to put in anything, especially with a nice little printed logo like that on there that doesn't go through those requirements as well. And that part basically, as a production demonstration, worked quite well. Showed that we could really push this material system into spaces where we're not using it currently. And completed that program. We actually took that 757, and the whole point of the eco-demonstrator program, particularly that one, was the sustainability. So we actually crushed the whole airplane. It was kind of cool. You can see it on the internet. They have some videos of it. Thankfully, we took that aisle stand out before we crushed it, because it wasn't worth throwing to the aluminum scrappers for that. But that was just a good opportunity to have to really kick the tires on it. Kind of shows you in qualitative terms, what technology readiness level you have when you can build something that big. that has flight control instrumentation in it, and you've got all your engineers looking at it. It's a good proving ground for the technology. So thanks for your attention. Anytime.